Yeah, thanks. You're right about ELPA. We had to go to Cuba and then we went to Jamaica because on a clear day we could see Cuba and there was some communist link. For anyone who's interested, we're planning to go to Tobago in the end of January next year for people who want to go to a conference in a nice place. We should have a call for papers coming out soon. So I think Yuri's talk was a perfect sort of precursor to mine, his historical, foundational, philosophical view of the past of this, whereas my work is sort of more contemporary, the future, practice, computer science oriented, in some sense trying to do something useful, as Yuri mentioned. I'd like to cast some doubt on Yuri's claim and Martin's support that the golden age of logic is over. I think that's viewing it from 100-year span. I see logic as being a much larger ocean, and we're just in one of the troughs of the waves. Because it's not what it was 50 or 70 years ago, it doesn't mean that it's dead. You've got to be strong, people. Let's keep going and do things. So what I want to talk about is the logic languages of the TPTP world, and I'll talk about what that is now. The original title was going to be the logics of the TPTP world. And then I realized I'd be talking to serious logicians and I was going to have my ass kicked. And so I changed it a little bit to protect myself. So what's this all about? I'll come back to my contents. So what is the TPTP world? For those of you, some of you will have used it or come across it. It's a project that started off as a collection of problems in clause normal form for testing automated theorem proving programs, clause normal form of first order logic. And slowly, like the octopus, it spread its tentacles to the solution library, which is a large library of solutions to those problems, which are useful to look at to find out how to prove particular theorems. A large set of standards to allow interoperability between tools and proofs and problems. Proofs and problems are all written in the same language standards. And so some ontologies where you can very precisely express what you know about a problem or what a piece of software has established about some set of formulae. So supporting all of that, there's some services and tools online. You can run everything online. Thanks to the American taxpayer, I have a server that allows you to use all of my stuff, run jobs, and really practically do something useful, we hope, or even you can do mathematics as well. Ah, shot for that one. The one thing Guillermo, I guess, was referring to was the system competition that started running in 1993 or 1994. The first time I ran it, I was at James Cook University up on the Great Barrier Reef. And now this year in Israel, in Tel Aviv, in Haifa, it'll be the 36th edition of the competition, which is it's amazing how hard people will work to win a little piece of plastic trophy. You give them a big grant and they sit down and do nothing. You give them a plastic trophy and they'll work hard for 6 months with no sleep. So at the moment, the TPTP World is one of the two platforms, some people claim the de facto platform, for supporting research and development in automated theorem proving. Of course, the other well-known platform is SMT out of the University of Iowa, which is also great works. So what I want to talk about today is the logic languages that are supported in the TPTP world, starting at the first order, classical logics, clause normal form and first order logic, moving up through various typed first order logics, both monomorphic and rank 1 polymorphic, then going on to typed higher order logic that's based on Church's simply typed lambda calculus, and then a little bit more, again, both monomorphic and polymorphic. And the latest developments hot off the press, which we haven't even released yet, and we'll be presenting in Haifa, are the non-classical logics, where we're extending the framework to support a whole suite of non-classical logics, starting off with modal logics that we all know and love, but certainly in a framework that allows people who've got their own favorite non-classical logic to express their formulae, their problem, whatever they want to model, using our framework and use the framework even without our direct knowledge of what they're doing. As I said, I made it logic languages sort of because I'm scared of logicians and I don't like Greek letters anyway. Sorry, Yuri, I know you showed me 22 of them. I was already nervous. So how does this link to John? So as people might hear from my accent, I did my master's degree in South Africa up to 1986 in graph theory and a little bit of mixture into computer science for the master's. And then I moved to Australia. I had to leave South Africa because I was about to be conscripted into the army. And I had a medical problem with going in the army. I'm allergic to bullets. I break out in holes. So I moved to Australia, to West Australia, where I got a job. And I started thinking about proving theorems in graph theory. And I was woefully ignorant, seriously ignorant. So I rolled down to the University of West Australia from where I was working up at the college. And I met Prof. C.P. Sang, and I'm sure some of the Australians out there will remember C.P. Sang, who realized I was ignorant and gave me books to read and told me to go away until I'd learned something. And I did. And I came back and he took me on, which was very great. And I was sort of getting mixed up with logic programming at the time, which is somewhat the link to John. Parallel and distributed logic programming, of course, Prolog was all about it, which led into in some way to the implementation of my thesis research, which was in linear resolution, as you know, came out of Don Loveland's crowd in Slagle. So after about 5 years as a part-time PhD student, Sang walked in one day and said, "Write your thesis and get me 2 examiners." I wasn't really sure how he knew I'd done enough because he was a pretty hands-off guy, but he was right. And I've really been struggling to remember who the other examiner was. I think it might have been Owen Astrakhan, but John kindly agreed to be one of my examiners. And when his report came back, he asked me to make changes in the thesis to add the linkage between logic programming and the linear resolution I'd been working on, which sort of closed the loop rather nicely because I've been using Prolog-based style in the TPTP world. So today's more effort then is, as we see here in this picture on the right-hand side, is this hierarchy of languages that I support, and I want to work my way through them. And this is really best if you understand the Garfield comics, you know, about the cat. If you don't, you'll probably get the drift as we go along. But before I get into Garfield, let's look a little bit about the basic style of the language that I use. This example over here, whoops-a-daisy, really is a sort of a very simple example in first order logic. And I'll look at, you can see the components of it. So the idea when we wrote this language, this is the second version, it came out in version 2 of the TPTP, was to make it human readable to whatever extent we can, machine parsable, really easy, flexible and extensible. And this was done with Christian Suttner from the Technical University of Munich, who helped me establish the TPTP language and the problem library and everything. As I mentioned before, the idea of the language is that it can be used for writing problems and solutions. So for writing both conjectures and proofs. And that allows you to pipeline a proof as an input to another tool so you can pipeline tools together. And so this is sort of one of my mantras because I'm not a deep sort of logician type, but I provide the syntax that you need. And as long as you provide the semantics, and then I'm happy. So as we see here on the right, this is a very simple example of an axiom. So we have out the front, the language. In this case, the language is a first order language. We also support clause normal form, typed first order form, and typed higher order form. Every formula has a name. We see there, that's the name as we see over there. And then what the formula is being used for. Is it an axiom, a lemma, a conjecture, a theorem? So we know something that the tools that are going to be manipulating this logic are going to understand what is its purpose within the input. Then the formulae, as we see here, it's Prolog-like. So people like Prolog, I like that. And the nice thing is with one prologue, read X. You can read one of these things with a few operator definitions. So the entire task of writing a parser completely disappears for students and beginners if they want to get into using automated theorem proving, writing an automated theorem prover. You don't have to spend the first 3 months writing a parser based on the grammar, which is, of course, available. You'll notice no Greek letters, only Roman letters. Anything that's on your keyboard are used. So that means you don't have to be an Emacs user doing Control Alt Meta Shift P in order to get a character out of it. You can just use your ordinary keyboard. All the connectives are written in ASCII, and of course we have built-in equality as a notion, a little bit of semantics creeping in there. So that's the basic form. So this one says for all X, A, and B, if X is a member of the union of A and B, that's equivalent to saying that X is a member of A or X is a member of B. I've got the optional stuff. It came out of a file, this formula, and some extra information. This is very free format and prologue-y kind of style. So if you get that sort of general style of the language, we can start looking at individual languages. I'm going to start at the top of this hierarchy, starting off sort of at CNF and FOF, and work through showing the more and more the greater expressivity that you gain as you go forward. And that's something I mentioned when I commented on Yuri's talk. When we're doing stuff in legal reasoning now, we're really finding that we need non-classical logics to do a lot of that. And if you want to reason in mathematics, a higher order logic is often useful. But for a lot of things in verification, like what Microsoft research people do, we're happy to sit down in one of these lower languages that have a typed system. And then right down at the bottom, of course, the classical first order stuff is what we know and love and should be teaching to every undergraduate in the world. So there's Garfield for you. So we all know about classical first order logic. My first order form doesn't really need an introduction. Surprisingly, there are not many automated reasoning programs that work directly in the first order form. There's Jeff Pelcher's Thinker, Dominic Pastier's Muscadet, and then it sort of falls away a little bit. And although this example's simple, just to make sure that everybody gets the drift of how these languages work, here's a problem. So we know that Odie is a dog. John is the owner of Odie. Odie's the dog, if people don't know the cartoon series. For all D, if D is a dog, then the owner of the dog is a human. Here we have, there exists a dog D, such that D is not Odie. John is not the owner of the dog, and that dog bit John. And we have for all D and H, if D is a dog and H is a human, and H is not the owner of the dog and the dog bit the human, then the human hates the owner of the dog. Very simple thing. Notice that all of these are axioms. And then we can very simply conjecture, this is what's to be proved by the automated reasoning tool, that there is some human that other than himself that John hates. And that's kind of easy stuff to do. And when I teach my courses in logic and automated reasoning, I give students these things in English to write that down. There's lots of people who do that. However, in the real world of automated theorem proving, the high-end people, first order form is not commonly used. If we bow down in classical first order, everything gets translated by an equisatisfiable translation to clause normal form using a proof by contradiction. So you take the axioms, negation of the conjecture, produce clause normal form of that and hand it over. And there are some well-known tools for manipulating clause normal form. Most of these tools have built into them the translation from first order form to clause normal form. I guess Vampire is the most famous from Andrei Vorenkov, also out of Novosibirsk. Stefan Schultz is very well known. There's E-System. And watch out, folks, here comes Zipper Position out of the Free University in Amsterdam. This is a real gun theorem proving program. I think it's going to take over. So as an example, you can see here, it's just the clause normal form. People are probably familiar with clauses. It's a disjunction of literals. And so, for example, this formula up here is translated into these for clauses. This formula over here is translated into this disjunction of literals. And that's what's being used as the assembly language, the internal manipulation of most modern automated theorem proving programs. Well, as we all know, without types, you're in trouble, particularly if you want to do arithmetic, if you want to do anything with numbers. And it turns out that for real world useful things, numbers pitch up all over the place. So you need to move up to a type logic. And as any good ML programmer will tell you, if the type system checks out, you've probably got your program right. So the next language is the TFF level, which has a monomorphic variant that's just simply multi-sorted logic, and a polymorphic variant. The 0 means monomorphic, 1 means rank 1, polymorphic. So what do we get out of this? That's Odie, for people who don't know the comics, that's the dog. So what do we add to first order logic in order to get a typed first order form? We add types, type signatures, and typed quantification of variables. All variables are given types. We give all symbols a signature, their argument types, and the result type, the usual business, and you have to be correctly typed. And once you've got this, you can start playing with numbers. So within the monomorphic variant, TF0, we support the type of individuals, the type of Booleans, 3 types of numbers, integers, rationals, and reals, and the user can define their own types through the T-type, which is the kind of all types, if you're thinking set theory stuff. So we have type signatures, and I'll show you some examples. The equality here and arithmetic is polymorphic in a simple way. For example, the greater function for arithmetic, you can put either a pair of integers, a pair of rationals, or a pair of reals and get a Boolean return. One of the nice features of our typed first order language is if you leave out all the type information, it degenerates straight back down to first order logic, untyped first order logic. And that turns out to be useful later on, having default typing. And so now we have to go up to some different theorem provers that can deal with the typed logic. So here's an example. Sorry, Odie's eating some of it. Just to give you an idea of what sort of things you can say. So here's an example. We're declaring that dog is a type over there, and here that human is a type, Odie is a dog, and John is a human. And here we see a type signature. The type of bit says it takes 3 arguments, a dog, a human, and an integer, and it returns a Boolean. So then in the formulae that follow, we can see that, for example, obeys the signature of bit because Odie is a dog, John is a human, and 2 is an integer. We also quantify variables. So here we see a formula with the variables quantified. D is of the type dog, H is a human, and N is an integer. This is the one to hate the multi-biter. So if H, the human, is not the owner of the dog, and the dog bit the human N times, and here we see arithmetic, and N is greater than 1, then H hates the human, hates the owner of that dog. So that gives you more expressivity. And in fact, I really thought that this was going to be the dominant language to support automated reasoning, but it turned out you need a little bit more, particularly with modern applications in verification, which will be the next layer up that I'll talk about. Not the polymorphic, but we do have a polymorphic variant of this, which adds type constructors, and we have a new type of signature of polymorphic signatures as well. I'll show an example. Again, different tools become available because some of the tools just can't cope with this polymorphism. This tool over here, Leo 3 out of the Free University of Berlin, is one of the ones that can really deal with the broadest range, including the non-classical logics. So if people are interested in using any of these tools, which are free on my website, as I've said, I can just email me and I'll give you a brief introduction. You can use that one and prove pretty much anything, modulo how long you're prepared to wait. I guess people understand that here theorem proving is semi-decidable, which means it's complete modulo control C. It runs until you press control C. So here's a polymorphic example. So here we see a type constructor, biter, which says it takes a type and you get another type out of it. So here, OD is of the type biter. It's a biter whose first argument is the type dog. Here we see polymorphism. So here, the type owner of is a function that takes a biter of some type and produces a human. So here you notice that we quantified over the type of the biter. So this could be, humans could be biters, or dogs could be biters, or cats could be biters. But in the use of it, here we see where's an example of owner of. In the use of it, you have to give as the first argument the type that is required. So the biter type is dog here, and then OD is of type biter dog over there. Again, here we see with bit, it's another polymorphic example over there, is that we have to provide the type is dog, which provides the instantiation for the polymorphism. And again, here's something nice. You can quantify over types. So for T of any possible type and B a biter of that type, we can now talk about that. So we have the example of polymorphism. Of course, this is useful for writing things down about data structures, lists and trees and all that, which is useful for verifications applications. As I said, I thought that was going to be the best. And I wrote this almost philosophical paper with Geoff Peltier, for those of you who know him, probably better known to many of you as a philosopher than a computer scientist, where we sort of, we said, what's going to be the right sweet spot? And I thought it would be this. And it turned out that the sweet spot at the moment is this next set of languages that provide a little bit more than plain sorted first-order form, typed first-order form. So that's normal for people who don't know the cartoon. So these are Fool formula. Fool was first written out by Evgeny Kotelnikov from Chalmers University, although I think it's been well known from long before that. He did it for his PhD work. What it does allow you to do is to have formulae, things of type Boolean, to be nested inside formulae. So you can have formulae applied to formulae, and you can have variables that are Boolean, which isn't available. Also, in this extended type or further form, we've added tuples, which are useful data structures, conditionals, that's if then else expressions, and let expressions that allow you to more concisely write things down when you're expressing your problem. What it is known and has been shown by Evgeny is that you can take any set of formulae written in this language and convert it down to plain TFF, which in turn can be converted down to plain FOF. And this is one way that modern tools for doing reasoning in TXF work. They just translate everything down and hand it over to one of the basic tools at the FOF level. So again, there's a monomorphic and a polymorphic variant of this language. And we start to see different tools playing around. So here's a monomorphic one. So the red again highlights what's new in this language. So here's an example of a predicate whose arguments, one of whose arguments is a term type, and one of whose arguments is another formula, and you get back a Boolean. So we see that over here. There's a nice example of the use of that. For all statements, so for all formulae, if John says that, then S is true. That's sort of like necessitation for necessitation by John for people into modal logics. Here we see again, John says that D, which is a dog, bit John 2 times. I mean, I haven't shown all the things that are available in this language, but here we see an example of a conditional. It's like an if then else statement, and these are real handy when you're talking about shadow variables in verification. So it says, if there is some integer n such that the dog bit the human n times and n is greater than 0, then the human chases the dog, otherwise the human feeds the dog. So if a dog bites you, you chase it, otherwise you feed it. So that gives you a little more expressive power. And I said it's this kind of thing which turns out to make this a bit more currently applied, because it's very useful in the verification applications. So now we can take the polymorphic ideas and the extended first order ideas, the full ideas, and put them together. And this is really just a union of the two concepts. And here's a formula where we've got, because remember, biter now is a type constructor. So we take the type constructor, apply it to a type. So D is a biter of type dog, H is a human. And there we see bit, which is now a polymorphic expression. Here we see the definition of bit. It requires a type. So the type is dog. So D is a biter of type D, of type dog, human and N, and that goes on as before. So now we've got a more expressive language. And one of the things I always fear when I start teaching this business, as I go through these, working up the hierarchy and showing students examples and trying to get them to understand it in a kind of a simple way at least, that slowly their eyes start to glaze over as things get more and more complicated. And I haven't really found a completely effective way to get rid of that glazing effect, other than to buy very cheap Coca-Cola from Publix and give it out to all of them at the beginning of the class, which tends to keep them awake. But then the next faculty who gets them on the downside of the sugar rush, and that's kind of cruel. So moving up a little bit more, I'm going to be good for time. This is really the point where people start to glaze over, I find, when you get into a higher order logic. And really for me, it took me a while to become more and more comfortable with higher order logic, because the abstraction is quite different from what you get if you haven't been taught functional programming. So if you've come up in the world of Java or Python, then actually I like all programming languages that begin with P: Pascal, Prolog, Python, Perl. But I don't like Python because I hate it telling me how to indent. Anyway, when you come up to this, then things start to hurt. So let's look at what these higher order languages offer. So what do we get here? That's John, by the way. So now we curry everything so that all types are curried. We have to have lambda abstraction with lambda terms, explicit application, and of course, application can be partial. So if you've got a function, you do a partial application, you don't give it all the arguments you want. What you get back is a lambda term that applies to the remaining arguments. You can use connectives as terms. So as well as saying A and B, you can say and applied to A, applied to B. And so something like and applied to false is a lambda term that always returns false. We can do that. And there's some extra binders for choice and description. That's definite and indefinite description up there. This is the one case where there has been a commitment in some sense to the semantics. We do Henkin semantics with choice. This is work done with Chris Bensmuller and Chad Brown. And at the time when I did this, I was really hazy about higher order logic. So I took their advice, and I'm grateful that it was good advice. And now I understand that once you've got Henkin semantics, of course, you also have Boolean and functional extensionality sitting out there. Again, we have monomorphic and polymorphic variants. What's quite nice now is that type signatures become types, and that allows you to use the type signature as the type of a variable that's quantified, either in lambda, universally, or existentially. And some different tools start appearing out here. You might see that vampire appears quite often. Actually, Leo 3 should be here too. There are others. I just gave some samples just to show that there are real tools out there that can really manipulate these kind of languages if it's the power of expressivity that you need for your application to do something useful. So it's the same sort of example about that, but let's look at what changes here. We now have owns, which is a predicate. It takes a human and a dog and produces a Boolean. So we see here the curried form rather than the uncurried form of the first order logics. Here's another curried example. Bit takes a dog, a human, and an integer and returns an O. Of course, so if you apply bit to a dog, you get a lambda term of type human to integer to Boolean. We also here use a notion of definitions. They're available in the lower languages, but turn out to be less useful there. So owns is defined to be the lambda term that expects a human and a dog, and it returns whether or not that human is the owner of the dog. Notice the @ here for application. And I know higher order logicians all immediately throw their hands up in horror at that @ sign there. Why don't you just put a dot or a nothing in between? And the answer is you can't parse it in Prolog if you don't have an operator, an infix operator in between. And I wanted everything to be Prolog compatible so that people didn't have to struggle writing parsers. And so explicit application with @. Here we see another formula. It says that bit applied to Odie applied to John twice. So Odie bit John 2 times. Here we see a signature being used as a type. This is what we want to say. What the idea of the intuition of this conjecture, given these formulae, is that if there's a dog that chases John and there's a human that's not John, then there is some function or some predicate F that is applied to John and the human. And of course, the predicate that you want to get out of this is hates over here, because that's what it is. Hates, John would hate. But here we have existential quantification. So we're out of first order world, we're up in higher order world, actually only second order here, but you know what I can do. And so we're saying that F is some predicate that applies human to produce a Boolean. These are quite hard to guess, of course. This is one of the things that makes higher order logic more difficult to automate, because you end up with flex pairs in the unification problem. All right, so that's the monomorphic variant. And then we can go polymorphic. So you just start mushing it all together. The only real change here is when you're polymorphic, instead of having to provide the types for all of your for all the types of a polymorphic symbol, you only have to provide some of them, and you get another polymorphic symbol out of it. Here we see Holy Hammer being used, one of the very few systems that can do TH1, Leo 3 vampire superposition. This etc. should probably not be there, because polymorphic TH1, not many people have really, I think those are the only ones that can do it. I'd have to look at my tool bank. If people are interested, I have about 82 different automated theorem proving programs installed on my system that you can play with if you like any particular one, including Otter from Bill McCune, for those people who remember the early days of automated theorem proving out of the Argonne group with Larry Wass. So here's another example, not much to say here. It's just mush things together. So owns is now a polymorphic symbol, as shown by this polymorphic binder, which takes a human, a biter of some type, the polymorphic type, and produces a Boolean. And now we see the definition of owns is now a lambda term that takes a type, a human, and a biter. B is the biter of that type, and human is the owner of the type for that biter. And you need to do type checking here, of course. If you can use ML type checking. Henley, I can't remember. Somebody shout out if you can remember it. And again, we have a very nice polymorphism available here that puts together the higher order aspects and the polymorphic aspects. So this, what's the use of this great, big, powerful language? What we've been looking at is the Isabel interactive theorem prover, and I do work with, that's Tobias Nipkoff and Jasmine Blanchett and all of that incredibly intelligent crew of people. And also Whole 4, they output proof obligations to be solved automatically and hand them down to one of these automated systems. For example, hole 4 hands off to the holy hammer, and sledgehammer hands off to mostly to zipper position these days because it's from the same group in Amsterdam. And it turns out to be useful in some contexts to be able to take the output from Isabel or hole 4 or cock and not reduce it to a monomorphic form through monomorphization, or even reduce it down to a first order logic through lambda lifting and combinators. How are we going for time? All right, very nice for time. So that's things that all exist. This is all available. The TPTP problem library has about 28,000 sample problems ranging across these 4 languages and their variants for people to look at. All of the problems are well documented and with references to papers and all the things you love. Maybe people want to see one. Yeah, let's look at, this should be your your homepage, tptp.org. All right, so just write that down. Because one of the benefits of having that as your homepage, it's just coming now, is that it gives you the opportunity to donate money to the project. But if you look at it, let's look at a very simple one in puzzles, the famous Aunt Agatha problem. You see here, it's documented, it looks like prologue, things that start with % or comments. So there's the English version of it, references to papers, and if you click it, you get the LaTeX. We have problem ratings. This is real easy. 0 means if you can't solve this, you should be doing social science. 1 means if you can solve this, it should be in your PhD. So this is a pretty easy problem, some syntax, and you start to see the formulae like that. So, and if you want to solve the problem, you can click one of these links over here. Well, before we do that, you can go and look at solutions. There you are. I told you I have a lot of theorem provers that have tried it. And if you want to see a solution, you can pop into one of these tools. Here's a solution by E, and there's the solution all printed out neatly. And you'll notice that the language used for the solution is exactly the same language as used for the problems. And then you can process the solution. All of these tools available. Here's the grooviest tool. Run the IDV tool. Stuff happening. Something should happen. Oh, there we go, it's loading it up now. So now you can look at the proof tree, and this is great for teaching notions of proof to students because they can see the formulae in first order form, the conversion to clause normal form, the inference steps leading at a false at the bottom with a proof by contradiction. What was I raving about? Okay, yeah. So now this is the latest thing that we're going to release. I hope this will come out in the spring of 23. We've only just released TXF, by the way. It's just coming out now in August. No, it came out already 2 weeks ago, another iteration in August. But now we're going non-classical because we wanted to be able to say more. This is Arlene the cat. So this isn't stable. We still might be some adjustments to the language here. But there's a first order non-classical based on the TXF language and a higher order non-classical based on the higher order forms that we have already. Again, with monomorphic and polymorphic variants. And we're a little bit unsure, sorry, that should say non-classical. We're a little bit unsure about what the semantics are of higher order polymorphic modal logic. I mean, what happens to the types as you move between worlds in the crypty semantics? I think it all works out, but the guys I work with in Berlin and Greifswald, who are better logicians than I, said, don't make any commitment. We're not sure if it makes sense yet. So take polymorphic with as many grains of salt as you wish. So one of the interesting features when you go non-classical, you cannot tell what logic you mean from the language. You know, let's say if we're in modal logic, the same language is used if you're reasoning in K or D or S4 or S5. And it depends what properties you want in the relationship between the worlds. And so one of the things you have to add into the language is an ability to express the properties that you want for the logic. And so here, at the moment, we're just playing with modal logic. And for example, constants are rigid, i.e. they have the same interpretation in every world. Quantification is constant. We also allow decreasing, cumulative, and varying. So we allow that for people into modals. And you can also specify either axiomatically or by systems. So this problem, if this little glitch over here with the role logic was put into it, this would specify the properties of the logic, the modal logic we're in, which then, of course, affects the reasoning that is done downstream. If people are very subtle and read the books by fitting, is our axioms by default are global, hypotheses are local, and conjectures are local, but you can override that. Of course, the idea of local versus global conjectures in particular is kind of obtuse, and so don't worry about it if you don't like it. So once you can specify the logic, you need some connectives, and we have this syntax, and this is the thing that might just change, because at the moment, the way it's written, it's not prologue parsable. And I cried my eyes, deep tears when we decided this. So I'm going to try and convince the other people involved we'll change it. But the sort of things we can say here, so this is a multimodal logic example. It's necessarily in the view of index Arlene, in Arlene's eyes, that this human hates the owner of the dog. So, and if something is necessarily true and you're in something above M, is it, or B, you know that it's true anyway, because necessitation leads to truth. Here's an example where we say something is possible. We also support box and diamond, box and dia. So if you like a shorter notation, you can use that as well. So as I said, this is really pretty hot off the press. And I'm interested in anybody who's interested in non-classical logics, would like to criticize, contribute, advise. We could really use some input here before we stabilize it and release this work as a stable product in TPTP version 9 in the spring of next year. So what's my conclusion here? I think the timing's about right. Is that right, Guillermo? Somewhere around now? So what did I talk to you about? It's the logic languages. These are the languages we support. And hopefully they are useful. Other people have found them to be useful for expressing things in a broad range of domains. And let me just roll back here. I wanted to show you this sort of thing.
Sorry, Geoff, yeah. 1 second only. So you have a little bit more of time because Yuri went over his time. So I was thinking that it was okay to give you a few more minutes. So don't worry about it.
You're right. Yeah. I've got about another 5 minutes max anyway. Thanks. All right. So the sort of problems. Oh, that's not the one I want. I want to say the documents. This is everything is very documented. So here you see the sort of areas in which we have problems encoded, starting from logic, as we know and love it. A lot of mathematics, in particular, algebra was very hot in the 60s and 70s. So the work done, a lot of people can encode algebra, and of course it can be encoded as unit equality problems. For people who know the AIM project of Bob Veroff, which is really dealing with open questions in mathematics using automated theorem proving. People might remember the Robbins problem that from Tarski, which says that every Robbins algebra is a Boolean algebra. And that was an open problem from when Tarski posed it up until 1980s or 90s, when it was solved by the automated theorem prover EQP, solved in the affirmative. So that was kind of like a hero thing in automated theorem proving world, that we could do what Tarski and his students could not. All right, and you see a lot of mathematics. A growing area, computer science, various forms, particularly things in the area of artificial intelligence, as we see around here. Science and engineering, biology, medicine, processes. We got a lot of stuff in products about how to make wine. Very nice, useful piece of reasoning about wine production. This is what I mentioned earlier to Yuri, social choice theory. We do management. We did work with people in Amsterdam looking at how businesses grow and expand and looking at properties of how they grow and expand in order to understand that and prove particular conditions that are necessary for the growth of a business. Some philosophy, and of course, down to the puzzles, many of which are thanks to Raymond Smullyan and his glorious book, What is the Name of This Book? So I gave that overview, showed you a bunch of the languages. One syntax, in general, it's Prolog compatible, except for the non-classical stuff. And I feel a little bit like John does here when I look at that. I've got to give thanks, of course, to Jim Davis, who provided me with all the pictures. I don't know him, I just stole them. So here's what I ask of you, logicians, the call to arms, call us babes in arms. Our languages are key to success, these languages. And the TPTP World really is the de facto platform. If you want to write down problems in logic and actually get proofs, not just talk about them, really do stuff, the TPTP World is one free way to get it done. And I'm here to help you as much as I can. We need you, at least for the semantics. So please contribute your expertise. And even if you don't, please contribute money. The funding's hard to get in logic and stuff, as many of you must know. So it's been going on, but a long time ago, I wrote a paper on this stuff with Christian Suttner, and this was about the best review I ever got for a journal submission. I really like this one, and I'll read it with you. Let me make it a bit bigger so it's easier to read. The reviewer, just like probably most readers of the AI journal, believe that the style of systems as compared here in the TPTP competition, search-based fully automatic theorem-proving systems, whose intellectual roots are still in the 70s and early 80s, are misguided, intellectually frozen in a time warp of the early days and only kept alive by a small, isolated, by a dedicated community. And this goes back to what I was saying at the beginning. Logic's a big ocean, and it really went down, and now we'll see it go up again. Have faith. Go, go, go. So they suggested that me and Christian, as the authors of this paper, were luring the youth into a style of work that is essentially wasted, and we should be forced to drink the poisoned cup of Socrates for corrupting the youth. I thought that was an excellent review, given that the reviewer also accepted the paper eventually. But it does show you have to persevere, and we start to see things happening. So I give thanks to the TPTP World users, the developers, the funders, and of course to Prof. John, who gave me passing my PhD, which led to my academic life and all of this work. I'll stop there. I can happily discuss this or demonstrate the tools and take questions. Thank you.